Let's take a look at number 5 here. Number 5 reads, magnetic resonance imaging, MRI, is a medical technique for producing pictures of the interior of the body. The patient is placed within a strong magnetic field. One safety concern is what would happen to the positively and negatively charged particles in the body fluids if an equipment failure caused the magnetic field to be shut off suddenly. An induced EMF could cause these particles to flow, producing electric current within the body. In other words, you might get a zap or electrocuted. That would stink. Actually, hopefully you haven't had to have an MRI done. Usually it's if you have migraine headaches or joint damage to a shoulder, knee, ankle, etc. But MRIs do give doctors very clear, accurate pictures of the body that you can't get with a traditional X-ray or CAT scan. Anyhow, for your safety, suppose the largest surface of the body through which the flux passes, the changing magnetic field, has an area of 0.036 square meters and a normal that is parallel to a magnetic field of 1 Tesla. Determine the smallest time period during which the field can be allowed to vanish if the magnitude of the average induced EMF is to be kept less than 0.01 volts. That's a mouthful. Basically, the idea is inside an MRI machine, you don't want, if there was a sudden power outage, for the machine to just shut down, because then you could induce an electrical current in your body with that changing magnetic field. So pretty much most hospitals would have some kind of backup system, backup generator, battery system to prevent someone from getting electrical currents getting induced in their body if there was a sudden power outage, because you don't want to electrocute your MRI patients there. So anyway, let's set up number 5 here. So in step 1, let's make a little picture. Inside an MRI machine, your body is put into a strong magnetic field, and basically you're bombarded with high intensity magnetic field on your body, and then that causes, I believe it's the hydrogen nuclei inside your body to go to a higher level, and then as the hydrogen nuclei come back down, they give off an electromagnetic field which the machine can pick up to give high resolution images. Okay, and in this problem, the idea was there's a certain area of your body where the magnetic flux is changing over time, and we don't want it to be too big so you get an induced voltage. So the picture is a little abstract, but we just want you to think about the idea of a changing field inducing a voltage inside a conducting area. In this case, it would be like your blood vessels and such. So in step 2, we need to break down what information was given here. The first number that was given in terms of quantity is the area of your body, and we're looking at 0.036 square meters. The next piece of information was the strength of the magnetic field, which was given as 1 Tesla. And magnetic field strength is measured in Teslas in honor of Nikola Tesla. Finally, we were given that the smallest time period is what we want to solve for, where this flux is changing the magnetic field. We're going to solve for time. Is our unknown in seconds. And what we need to know is we need to keep it less than 0.010 volts. Okay? 0.010 volts. And normally, we would call this voltage, V, but in terms of magnetic fields and such, this is actually called the EMF, for electromotive force. What Faraday discovered, that when you change a magnetic field inside a conducting coil, you generate a voltage. Okay? So now we can apply Faraday's law from our electromagnetic toolbox, that the induced electromotive force, the voltage, depends on the number of coils in a loop, and the negative sign is actually a consequence of Lenz's laws. It's an opposing field to conserve energy there, times the area of the loop, times the change in the magnetic field, over the rate of time. And we should add in a little delta right here for the changing field there. Okay? So now, as you can see, this problem is pretty straight up. We just go ahead and substitute in our information there. Okay? So the voltage, we want to be less than 0.01 volts. That's equal to the opposing change of the changing flux. Now, N is the number of coils, and in this case, we're not telling how many coils are in this surface, so we're just going to assume it's 1. Okay? And then the area of the body is 0.036 meters squared. The strength of the field is 1. And then the time is what we're solving for. So the numbers given here are pretty simple. So to solve for time, I'm just going to do a little bit of algebra by bringing time up and dividing by 0.01. So basically this will be equal to 0.036 times 1 over the voltage that we don't want to have there. And the negative sign I don't have to worry about because it just means it's an opposing field there. Okay? So if I get out my calculators and plug in, this is actually pretty easy. It's just 0.036 over 0.01. It'll be 3.6 then seconds is our final answer. So, in a nutshell, that's number 5. It wasn't really a hard problem mathematically. It was just trying to identify what all the variables were and what the question was asking. So, number 5, in a nutshell.